Yeah, shall we start? Almost 3 minutes are getting over. Ten of them will join. I think so. You asked revision classes, right? For organic chemistry, you asked revision classes. What today I'm going to give you the revision for organic chemistry. So here, just I'm going to give you some questions. Whether you can able to solve this or not, you can check. If this compound, which is reacting with HBr, what kind of product I can get? What kind of product I can get? Can you able to hear me?
Yes, sir.
Sir, is it CH3, CH2, C, CH, BR, and CH3, sir?
CH3,
CH2,
and CH2.
CH. So there will only be CH, sir.
CBr.
CBr. Okay, good.
Oh, yes, sir.
What kind of rule it follows?
Sir, Markovnikov.
Markovnikov. Okay. The same reactant in presence of HBr as well as peroxide. What kind of product I can get?
Sir, it will be CH3, CHBr, CH3, sir. CH3. Anti-Markovnikov.
Yeah.
Sir.
Yeah, this follows the anti-Markovnikov.
Yes.
So as we know that the dipole moment, the next question is the dipole moment of chlorobenzene. Chlorobenzene is lower than that of cyclohexyl chloride. Yeah, explain. So how will you explain this? So dipole moment of chlorobenzene. So we know that the chlorobenzene, the structure of chlorobenzene, we know that. Okay, and we have to write both the structures of a chlorobenzene as well as cyclohexyl chloride. This is called a chlorobenzene, and this is the structure of cyclohexyl chloride. Yes, which will have more strong bond here. That's it. So the dipole moment of chlorobenzene is lower. They told us that is lower. Okay. Why it is lower? That's the question. So dipole moment in the sense charge into distance, we know that. Okay, charge into distance. So distance, no problem with that. Here the distance also will play some role and charge also will play some role. So what is the role here? So they said it is a lower than. So dipole moment of chlorobenzene. So for that cyclohexyl chloride, it has higher dipole moment. Why?
Sir, is it because of the number of bonds?
Number of bonds. Okay. Any other thing? Good. Okay. I ask you a question. That is, what about the hybridization of these two carbons? I can make it in another color. This is in pink color and this is in orange color. Okay. So chlorobenzene, what is the hybridization of that carbon?
SP2.
SP3, SP2 or SP?
Sir, SP2.
Yeah, it is SP. SP2. What about here?
Sir, SP3.
SP3. Okay. Then which will have more S character? SP2 or SP3? Which will have more S character?
SP2.
SP2. So why? So because 100 divided by totally 3 orbitals I have taken. So 33.33 percentage. Okay, each has 33.3 percentage. So s orbital only one is there, and remaining two are p orbital. So s orbital character says character is 33.33. But here sp3, so 100 divided by 4, totally 4 orbital, 1s 3p. So totally 25. So 1s here, so s character is 25 percentage only s character. Okay, so more is the s character, more is a stronger bond. Okay, moreover it can form partial double bond character also, so that its negative charge is very less, and here the charge is more. Okay, the negative charge is more here, that's what it is. It has higher dipole moment. Okay, this kind of question will also have. Okay, another thing is CH3, CH2, OH, alcohol I have taken. Here I can use SOCl2. So the same alcohol I can use PCl5 also. Okay. So what kind of product I can get when it is react with SOCl2?
Be CH3 CH2Cl plus HCl plus SO2.
CH2Cl plus
HCl
okay.
plus SO2.
So what about here?
Or it will be CH3 CH2 Cl plus again HCl.
POCl3.
POCl3 plus
Very good.
HCl.
Then HCl. Right.
HCl.
Okay. Among these two reagents, which is a better one?
The above one, because both HCl and
Sir.
SO2 are
Why? Why this is better?
because HCl and SO2 are gaseous.
Yeah, both are gaseous products, so we can get pure ethyl halide. Okay, ethyl halide we can get it. CH3, CH2, Br, and that is going to react with aqueous KOH. And the same thing will be reacting with alcoholic KOH. What kind of products it can be? Aqueous KOH and alcoholic KOH.
And for aqueous KOH, CH3 CH2 OH will be formed.
Okay. Alcoholic KOH. Alcoholic KOH. So it's a SM reaction, nucleophilic substitution reaction. So elimination. Elimination reaction means what? So I'll get alkene as a product. Okay. So alcoholic KOH, say for example, C2H5OH. If it is react with the KOH, then what it will give? So it's a weak acid, strong base. So C2H5OK, very strong base I can get formed along with that water. And this will be acting as a base here. So and then this base which is going to attack. So if it is an alcoholic KOH means there is an elimination reaction. You know the trick of elimination reaction. There is CH3, CH2, Br is there. And if base is coming and attacking that, so which base where it is going to attack in this compound?
Hydrogen.
Which hydrogen? Because here also we have hydrogen, here also we have hydrogen. Which hydrogen is going to attack?
I think the CH2 one.
No. So always it attacks a beta hydrogen. Okay. So the hydrogen can be plucked from beta carbon. This is alpha carbon, this is beta carbon. Okay. So usually we said that the rule is, so alpha carbon, from the alpha carbon, halogen is getting eliminated. From the beta carbon, the hydrogen is getting eliminated. This is what the reaction is called, dehydrohalogenation. Dehydrohalogenation. Okay. Dehydrohalogenation. It's a very, very important reaction. Okay, suppose if I want to prepare CH3, CH3, CH2, C, CH3. Here also CH3 and here Br. If it is reacting with aqueous KOH, sorry, alcoholic KOH, what will be my major product?
Is it CH3, CH2, CH3, CH3, OH?
Okay.
Yes,
So
sir.
if I use alcoholic KOH, it always form elimination product. But you're telling us a substitution product.
So, sir,
But
then
alcoholic
here
KOH,
we-
once we use alcoholic KOH, we will get elimination product only.
Okay.
Yes, then please. Yeah. We don't form instead of Br, OH is not going to attack here because it's not a substitution reaction. It's an elimination
Okay.
reaction. Just now I told you elimination reaction means from the functional group attached to carbon alpha carbon, and here it is a beta carbon, here also beta carbon, here also beta carbon. Okay, alpha next to alpha carbon is called beta carbon, next to alpha beta, next to alpha beta, next to alpha beta. I can number it as 1, 2, 3 also. Okay. But the question is, what is a major product? How can we predict? So you should remember the Zaitsev rule. Zaitsev rule. Okay. Yeah. So which kind of product I can get? What are all the possibility? If beta 1, the hydrogen is getting eliminated, what kind of product I can get? From alpha carbon, bromine is getting eliminated. Beta 1 carbon, hydrogen is getting eliminated. That time CH3, CH2, C, double bond, CH2. Here CH2. Okay. If it is beta 3, again the same product. Instead of top, we have a double bond in bottom. So CH3, CH2, C, CH3, here double bond, CH2 for beta 3. For beta 2, what kind of product I can get? CH3, CH double bond, here C, CH3, here also CH3. This kind of product. Is that clear? Out of which is a major product? Which will be the major product? How to find the major product of alkenes? So major product of alkene can be checked out by the help of number of alpha hydrogens. So if you compare this is a functional group. Now the double bond is a functional group here. Here the double bond is a functional group. How many alpha carbon? Now this is alpha carbon, this is alpha carbon. Here this is alpha carbon, this is alpha carbon. So here alpha hydrogen, 5 alpha hydrogen is there. Here also on this compound 5 alpha hydrogen is there. But what about here? How many alpha hydrogens are here? How many alpha hydrogens are here? First you find out alpha carbon, then you can find out alpha hydrogen. The double bond is a functional group here. So the double bond attached to carbon, you should not count it. So the double near to the carbon, this is alpha, this is alpha, this is alpha. So each alpha carbon have 3 hydrogen atoms. So we have 9 alpha hydrogen. So more is the alpha hydrogen. More alpha hydrogen, more stable. Okay, more stable. So more sterically hindered. Steric hindrance, more stable, or more crowded. We can say other words, crowded, also more stable. So according to the concept beta 2, so if this will be the major part. This alkene is formed major. Okay. And, okay, will you prepare benzene to biphenyl? How will you convert this? So I'm having a benzene. From benzene to, I have to prepare biphenyl. Yeah. It's a two-step process.
What's the big reaction?
Yeah, yeah. How we can do this?
I think first of all, you should react. First is react
Yes.
with Cl2, right?
Cl2, very good. Cl2 in the sense, in presence of light or in presence of catalyst?
Catalyst.
Catalyst. So FeCl3, AlCl3. So what kind of product I can get?
HCl.
HCl as well as chlorobenzene. Am I right? Good. Then from this chlorobenzene, how we can convert this as a biphenyl?
With a metal, right? Na.
Sorry, Kana?
With a metal Na.
Yeah, with the metal Na. Sodium. Yeah. 2 moles of the same compound will be taken. So I can write like this. So chlorobenzene, it is react with metal, again Cl, and it removes to NaCl, and the entire reaction will be conducted in presence of ether, dry ether only. So I can get formed biphenyl as a product. I can get formed this product. Okay. Suppose the next question is Grignard reagent. Grignard reagent should be prepared. Should be prepared from under anhydrous condition. Under anhydrous condition. Why? Grignard reagent always used to prepare under anhydrous condition.
It is highly reactive, so it will react with moisture.
Okay, if it react with moisture, what will happen? Right, you're right. CH3, CH2, MgBr. So we know that RMgX, that's a Grignard reagent. If it is react with in presence of moisture contact or water, what will happen? The water will have H plus and OH minus. And here we know that the charge of this carbon is negative. Why? Because it is attaching with divalent cation. So then here also I have a minus charge. Also I have a positive charge. So then CH, this minus charge will approach this and this positive charge will approach this. Then what will you get? CH3, CH2H along with that Mg, here OH, here Br. So, yeah. So I can get formed the alkane as a product. So I can get formed the alkane as a product. That's what we should not prepare. We should not use any anhydrous condition. Okay. How will you make chlorobenzene to toluene? Chlorobenzene to toluene. Any idea? Cl. Again, the sodium metal.
CH3.
Reaction. Wurtz-Fittig reaction. In presence of ether, I can get formed.
Toluene.
NaCl will go off. So I'll get my product as toluene. That's it. Suppose if I want to prepare this kind of conversion, suppose CH3, CH2, OH. I have taken alcohol. From that alcohol, I have to prepare CH2, Br, then CH2, Br. How will you prepare this? So first of all, what we have to do? We have to convert this into alkyl halide. Okay. First of all, you have to convert this into alkyl halide. How we can do this? Either we can react with PCl3, PCl5, or what is that? SOCl2. We can convert this into alkyl halide. Sometimes in question paper, these kind of reagents will be given. That is a red phosphorus as well as iodine and the heat. This kind of things also be given. This is nothing but which forms, even if these two are reacting, it forms Pi3, phosphorus tri. That means triiodopa. Okay, you get like that. Phosphorus trichloride like that. Phosphorus triiodide, I can get it. So when this triiodide is getting formed, so what will be my product? My product will be CH3, CH2I. Okay. After converting this, what I can do? So, but I need to substitute here in two places Br. So definitely it should be an alkene. Okay. Then we can do bromination with the CCl4. We can do this. Okay. Just a minute. Yeah. So here I can use alcoholic KOH. We use alcoholic KOH. What I will get from the alpha carbon functional group is the string, from the beta carbon hydrogen is goes up. So CH2 double bond CH2. I can get ethene as a product. Once I got ethene as a product, then what I have to do? So I have to react it with Br2. Br2 in presence of CCl4. I can get form these kind of dihalogen derivatives of ethene. Okay. Aqueous KOH, alcoholic KOH, we discussed about that. Yeah. Suppose double bond here. Here it is reacting with Br2 in presence of heat or light. What kind of product I can get? Whenever the heat or light will be used, there will be a monohalogenated product. It always produces monohalogenated product. So either I can get the Br is getting substituted either here or here or here or get it here. Okay. So except the double bonded position, all the positions are occupied. Either you can give these kind of possibilities. Yeah. 1-iodobutane. So I need to prepare 1-iodobutane from but-1-ene. How we can prepare this?
So from but-1-ene, we can react it with HBr in the presence of peroxide.
Okay, but-1-ene, which will be reacted in the presence of good. CH3, CH2, CH, double bond CH2. Okay, it will be reacting in presence of HBr. Am I right? In presence of peroxide. Okay, what kind of product I can get?
I'll get CH3, CH2, CH2, Br.
Yeah, after this.
Now I can react it with NaI.
Very good. So
In the presence
NaI
of
as well
acetone.
as acetone. We use the NaI acetone, I can get product. I can get formed one iodobutane as a product. Okay. Okay. Now the question. Which of the following alkene? Which of the following haloalkanes reacts with aqueous KOH most easily? The answer number 1 is 1-bromobutane. 1-bromobutane. Answer number 2 is 2-bromobutane. Answer number 3 is 2-methylpropane. 2-methylpropane. Answer number 4 is 2-chlorobutane. What will be the answer? Aqueous KOH. Aqueous KOH means it's a SN reaction. Okay, nucleophilic substitution reaction. Yes. React with aqueous KOH. So it's a nucleophile. Yes. So usually, which reaction will be preferable? Can most easily can react. So 1-bromobutane, what is the degree of this compound? 1 degree. 2-bromobutane, 2 degree. 2-bromo-2-methylpropane, that's a 3 degree. Again 2-chlorobutane, 2 degree. Now we know that aqueous KOH means preferentially involving in 3 degree alkyl because that forms more stable 3 degree carbocation during the course of the reaction. That forms more stable carbocation. That's what the answer C is the answer. It's 2-bromo-2-methylpropane is the answer. Okay, so you can answer. Boiling point of iodobenzene. Yes, higher than that of chlorobenzene or bromobenzene. Whether it is true or false.
True.
True, right? Why? True only. Why, Kana?
Iodine is larger.
It has more surface area. So if it has more surface area, then it can accommodate more number of iodobenzene molecule like that. So molar mass is getting increases. The molar mass is getting increases. Boiling point will also get increases. Right? Okay. This is a compound CH2, Cl. What is the IUPAC name of this compound? IUPAC nomenclature. Can IUPAC nomenclature? Why it will take more time? So this is a long chain. So this is a first carbon, second carbon. So 1 chloro, 2 phenyl, ethane. 1 chloro, 2 phenyl, ethane is the IUPAC nomenclature of this one. Is that clear or no?
Yes.
RI, RCl, RF, RBr. Is it a right order of boiling point? Boiling point order. Is it a right order or not?
RF should be the last one.
RF will be in last. So it's wrong. Okay. Wrong order. It's not wrong. It's not a right order. Okay. And when RX is reacting with the KCN, it forms RNC as a product. Is it true or false?
False, right? For AGCN, we'll get RNC.
Yeah, it is false only because when REX it is reacting with AgCN only, it forms RNC as a product. So otherwise it can form RCN as a product. That's a right product, but RNC is a wrong one. Okay. Okay. Yeah. Suppose here one Br is there. Here CH3ONA I have taken, and I'm using aprotic solvent. Aprotic solvent. You just predict whether SN1 reaction, SN2, or E1 or E2 reaction. In which reaction this reaction is possible? Either SN1 or SN follows which kind of mechanism? SN1, SN2, or E1, E2? What are all the clues? If it is a aprotic solvent, what are all the categories we are using aprotic solvent here?
SN2 and E2.
SN2 and E2. So it definitely not be a SN. So either SN2 or E2. So SE1 and SN1 is strike out. You can strike out those. Whether it is involving in SN2 or E2, which possibility is there? That entirely depend on whether it can act as a nucleophile or it can act as a base. If it acts as a nucleophile, it forms SN2. If it acts as a base, it forms E2. Okay. Suppose the CH3O minus, if it acts as a nucleophile, then what it will do? What kind of product I can get from here?
Version.
Yeah. But act as a nucleophile. See here, what is the role of nucleophile? What is the difference between nucleophile and base? All the bases are nucleophile. All the bases are nucleophile. Okay.
Nucleophile
But
is
the
a
thing
base if
is,
it attacks hydrogen.
yeah. If it attacks carbon, then it acts as a nucleophile. If it attacks a hydrogen, then it acts as a base. That's the difference. Okay. That's fine. Good. Here, CH3O minus can act as both nucleophile act as well as a base. Now, here, if it acts as a nucleophile, what kind of product I can get formed? That's the thing. Carbon halogen is there, and if it nucleophile is there, nucleophile will go and attack where the functional group is attached. That carbon only it will be getting attached, and it will cleave off the halogens. Okay. By the way, the nucleophilic substitution reaction will proceed. But in the case of the elimination reaction, it's not like that. The base will always attack the beta carbon because it always attacks the beta hydrogen, and the halogen is getting eliminated from the alpha carbon. Okay. Yeah. Now you can tell me which kind of product I can get. If it acts as a nucleophile, what it will do? The nucleophile will go and attack where the functional group is directly attached. That's what I tell you. Nucleophile will attack the carbon which is attached to the functional group directly. If it attacks, then Br will get replaced. I'll get OCH3 as a product. And in the case of elimination reaction, so here we have a 2 beta carbon. Am I right? Beta carbon. This is also on beta carbon. This is also on beta carbon. Am I right? So I can write once again. I can write it once again here. So here, yeah. If you have a structure like this, here Br is there, and here beta carbon, and here also beta carbon. Am I right? So here beta carbon containing 2 hydrogen. Here also this beta carbon containing 2 hydrogen. So according to the concept, base will always attack beta hydrogen. Either can attack beta 1 or can attack beta 2. If it attacks beta 1, what kind of product I can get? So if you consider this as a beta 1, so I can get my product like this. The double bond will be formed here. So because from the alpha carbon, halogen is getting eliminated, from the beta carbon, hydrogen is getting eliminated. So I can get product like this. If it is beta 2, what kind of product I can get? I can get a product like this kind of product, because for this functional group, this is also beta, this is also a beta carbon. So either can eliminate it from there or can eliminate it from this. Okay. And here one of the important exceptional cases there. So what kind of important exceptional case? Say for example, suppose if I'm taken this kind of molecule like OH, okay, and this will be involving the reaction with H2SO4. Presence of H2SO4, the reaction will be taken. Heat will be applied and using protic solvent also. These kind of clues are given, whether it involves SN1, E1, SN2 or E2.
SN1 or E1.
SN1 or E1. Okay, good. Why? Because we used a protic solvent. So if you use protic solvent, SN2, E2, because for SN2, E2, we are using a protic solvent. Okay, for E1 and SN1 only, we are taking protic solvent. That's what good. So we found that either it involves in SN1 or E1. Another important clue is to find out the reaction. What is that? It's an important difference between the SN1 and E1 reaction. What's the important difference? Is the important difference heat. Usually SN1 reaction will be taking place at ordinary temperature. Ordinary temperature or normal temperature, but E1 reaction, elimination reaction will be carried out at a high temperature. Like high temperature in the sense when compared to that SN1 reaction will be high, almost 50 to 80 degrees Celsius only. So that much of not that much of very high temperature. When 50 to say 80 degrees Celsius, the reaction will happen. And one more, if it wants to run E1, what kind of things we have to use? Base we have to use, but here use a hydric acid. That is what I told you. It's the exceptional case. Okay, only in the case of alcohol with acid, that time only we can get elimination reaction by the way of dehydration. Okay, dehydration. Through the dehydration, this process will be taken place. It's an important exceptional case. Okay, and here if I'm taking a chlorobenzene, just I want to convert this into chloro and orthochloronitrobenzene. Yes, what kind of reagent I have to use? What kind of reagent I have to take? What kind of reagent?
Nitrating mixture.
Sorry, ma?
Nitrating mixture. HNO3
Nitrating
and
mixture.
concentrated sulfuric acid.
Concentrated HNO3 and concentrated H2SO4. Both we have to take. Okay. That's a nitrating mixture. We have to use this nitrating mixture. So then only we can get a nitro-substituted product because it's an electrophilic substitution reaction. And preparation of alcohols. So the alcohols can be prepared by two ways, right? By acid catalyzed alcohols prepared by two ways. What are the ways? Acid catalyzed hydration. Another important method is hydroboration oxidation. Hydroboration oxidation. Okay, what is the difference between these two things? Acid catalyzed hydration and hydroboration oxidation. In acid catalyzed hydration, we can able to prepare, 2 degree or 3 degree alcohols. I can able to prepare. But in the case of hydroboration oxidation, I can be able to prepare 1 degree alcohols. That's an important difference. And any other thing?
In the first one, it's indirect addition of water. I mean,
Very
first
good.
one, it's direct addition. Second
First one is a direct addition or indirect addition?
The first acid catalyzed is direct and
direct addition. Very good. Direct addition of water. Addition of water. But here it is an indirect addition. One more difference is there. Any other thing? One more difference. Very good. Good try. Direct addition, indirect addition of water, because here we are not going to add any water here. Here we used sodium hydroxide and peroxide. In presence of borane, diborane, we can use it. It follows Markovnikov rule. Yeah, Markovnikov rule. It follows anti-Markovnikov. That's another difference. Okay, Markovnikov and anti-Markovnikov. Oh, very good. Okay. Suppose if I want to prepare alcohols. Okay, what kind of alcohol? Say for example, I'd like to prepare alcohols from this CH3, CHOH, and here CH3. Okay. Then from the 3 carbon containing ketone, how we can do this? So here I gave reactant as well as product. What kind of reagent I have to use? So whether it is oxidation or reduction. From ketone to alcohol is oxidation or reduction? It's a reduction. Okay, why? Because one hydrogen is added here, one hydrogen is added here. That's what we have hydrogen. So addition of hydrogen is nothing but reduction. Okay. Here one hydrogen, one hydrogen. So reduction. Sorry, now what kind of reagent? Good.
LiAlH4.
Very good. Lithium aluminum hydride I can use. Otherwise, NaBH4 I can use. Or otherwise, palladium hydrogen I can use. Platinum hydrogen. So all these reagents can be used to convert from ketone to alcohol or aldehyde to alcohol. We can use this. Suppose the reagent will be given like this: CH3, C double bond to OH. So here also I have to prepare CH3. Okay, if I used lithium aluminum hydride, what kind of product I can get?
RCH and 2OH.
CH3, good. Then
CH and OH.
CH2,
CHOH.
CHO. Okay. So here I get formed alcohol as a product because lithium aluminum hydride is a very strong reducing agent. So it can convert. Initially, it will move towards to aldehyde only. So it can form first aldehyde. After that, only the alcohol is getting formed. But here, lithium aluminum hydride is a strong reducing agent. That's what it can convert directly carboxylic acid into alcohol. Okay. Whether we can able to use NaBH4 here.
NaBH4 is only for aldehydes and ketones.
No, we should not use NaBH4. NaBH4 used only for aldehydes and ketones. Okay, not for carboxylic acid and its derivatives. But NaBH4 is a special compound which is used for reducing this acyl chloride. For this compound, we can use this NaBH4, but other compounds we can't use it. Okay, that's the only exception. So NaBH4 is a weak reducing agent. It can use to reduce only aldehydes and ketones, not for the carboxylic acid and its derivatives, except acyl chloride. Okay. And another important thing, say for example, CH3. How will you prepare CH3 MgBr2 CH3 COH CH3 CH3? Yeah, how will you make it? 2-methyl propan 2-ol we have to prepare by the way of reacting it with Grignard reagent. Yeah. How can we do that? Just indirectly I'm asking.
It's with ketone.
Ketone. What kind of ketone I can use?
CH3 C double bond O CH3.
CH3 C double bond O CH3. Am I right? Very good. So I can use this. So if I use this, I can get this product. Why? Because we know that whenever the Grignard reagent is used, that carbon will also be attached to this. Okay. So if you want to prepare one carbon or number of carbon containing alcohol should be higher than that of that reactant what we have taken. So that time you have to use Grignard reagent. Okay. Say for example, if you use here I can get this product. So from that reactant, we know that here 3 carbon atoms are there totally. Here 1 carbon atom. For the product, we can get 4 carbon atom containing product. Okay, we know that if 1 degree, if aldehyde is reacting with this, if aldehyde reacting with RMGX, what kind of product I can get now? I can get formed what kind of product? Which kind of alcohols?
2
You can
degree.
get 2 degree alcohols. Very good. So if ketone is reacting with this same RMGX, then what I can get? 3 degree alcohol. When I will get 1 degree alcohols?
HCHO.
Only with formaldehyde. Okay, only formaldehyde with RMgX. So I can get formed the 1 degree alcohol. These are all the important chart. So you should know all those things. Okay. So when aldehyde except formaldehyde, all other aldehyde will forms 2 degree alcohols only when it is reacting with the Grignard reagent. Okay. Okay. CH3, C double bond O, CH3. And the same reagent, it will react with the two different reagents, LiAlH4 if it gives. If it is giving with the CH3, MgX. Yes. What are all the products? In the first case, second case. Yeah.
The first case
When I use lithium aluminum hydride, I can get
degree.
same number of carbon containing alcohol is getting formed. Okay, CHOH and here CH3. When I use Grignard reagent, so we can use here 3 carbon, here 1 carbon, totally 4 carbon containing alcohol I can get. Okay, this is a very important reaction. So whenever if we want, we can ketone, from the ketone we can able to prepare 2 degree alcohol as well as 3 degree alcohol when you, while you changing that reagent. If you change the reagent, so the entire thing will change. Okay. Okay, and here which is more acidic? I'll give you RCH2OH, and one more thing, RCHOH. Here also RCRROH. Here all R is nothing but CH3. Yes, if they given like this, yeah, you just find out the acidity. Acidity of that acidity order you can, it's just more acidic. Which alcohol is more acidic? Because it's nothing but it is primary alcohol, secondary alcohol, tertiary alcohol. Yes, that's the difference. Yeah.
1 degree is more acidic than
1 degree is more acidic. Very good. 1 degree is more acidic, then 2 degree, then 3 degree. Why? Because we know that acidity is nothing but removal of H plus. H plus ion wants to remove that oxygen. They should have more tendency to attract electron. That means it should have higher electron. Okay, but here the electron donating group like a methyl group will donate electrons. But that's what the negative charge on this oxygen is getting, somewhat is getting reduces, so that the acidity will affect. But in this case, there are 2 donating groups. When compared to this, this will have more electron. Okay, on oxygen. And here also same thing. 3 donating groups are there. If there is 3 donating groups, the oxygen will always will be satisfied. Okay, oxygen will take out the electron from this methyl group. It no need to take electron from this hydrogen. If it takes electron from the hydrogen only, the H plus will come out. Okay, likewise. So the 1 degree alcohols are more reactive than more acidic than 2 degree and 3. So about the acidity. And okay, the very important thing is so I have alcohols like this. Okay, so this alcohol is formed from which alkene? Which type of alkene it is formed? So for that, what you have to do? Alcohol to alkene. So we know that alcohol to alkene and alkene to alcohol. You know that both the reaction mechanism, right? So here it is a dehydration mechanism. Am I right? And it is a hydration of alkene to alcohol. So here alcohol to alkene, because alkene to alcohol they ask, but we have alcohol. If you do dehydration, you can find out alkene as a product. Okay, if you do dehydration, what will happen? So if you do dehydration presence of acid, what will happen? The oxygen will donate electron. Then what I will get? I'll get a structure like this. So here O, here CH3, here H, here H, and oxygen got positive charge. That's what it will be eliminated as neutral water molecule. Then I got a positive charge because oxygen will take over the electron from this bond. Oxygen will take over the electron from bond. So this will get positive charge. And here I have CH3 group also. And remaining things are same, right? And if I got positive charge and hydrogen here, it will left over as H plus and it can donate it to electron pair. So what I will get? I'll get alkene as a product along with that CH. Okay, this kind of alkene. This is the structure of alkene is getting formed. So if you have any doubt, you can do it with if you add water, it follows Markovnikov. So if it follows Markovnikov rule, the same OH group, that is, if you do again hydration, HOH. So if you do, because it's a unsymmetrical alkene, right? It's an unsymmetrical alkene. If it is an unsymmetrical alkene, it follows Markovnikov rule. H plus OH minus. Now where OH minus, where it will go and approach, where the lesser number of hydrogens present. So here in this two carbon, here CH is there. Here instead of one hydrogen only, the methyl group is attached. So that lesser number of hydrogen path is this. So that OH minus will be attached here only. That's what I can give this. Is that clear? Is that clear, Kana?
Yes, sir.
Yeah, after which we'll stop, Kana. We'll see next class. Okay. So today I want to go to hospital. I told you, sir. So I can stop with 1 hour. Okay. Hello.
Thank you,
Okay.
sir.
Yeah.
Thank
Thank you. Bye. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Daddy, kill him,